Okay, so then it becomes, all pixels become closer in value to each other, whereas a high value of contrast, the pixels will move farther from each other, right? Okay, so the technique that I used over here for the contrast was pretty simple. Okay, a better way to accomplish contrast is through what we call this. Okay, so better way to accomplish contrast is through what we call histogram equalization. Okay. So how does this technique work? The fundamental idea is very simple. Okay. What we do is first we create the histogram. Okay. So what exactly is a histogram? Histogram is basically on here is basically the frequency or the count. Maybe frequency is not the proper word, let me say just the count. And here is the pixel value. Okay, for example, let's say we have some, and for the time being, let's focus on grayscale. Okay, meaning red, green, blue pixels are all the same. Okay, let's say here's a pixel value 55, 55, 55, 55, 55, 55, 55. So let's say the pixel value 55 appears 1, 2, 3, 4, 5, 6, 7 times, right? So here, where it's 55, this value will be 7. Okay. Let's say there's another pixel value, 100, 100, 100, 100. Okay, it appears 4 times. So somewhere over here is 100. So it will be 4 times, right? So anyway, in the end, basically, you'll see we'll get some kind of graph over here for how each and every pixel, how many times it appears. Okay. So when we have a low contrast image, then what does that mean is that majority of the pixels are close to each other. Okay, so they could be high in value, they could be low in value. For example, let's say you took a picture and majority of the pixels are between 150 to 180 range. Okay, so whatever that picture is, okay, because it is, see the higher the number, there's a little bit of a whitish or the brightness in it. If lower the number, it will be a darker picture, right? So whatever the scene is, doesn't matter. Okay. Okay, so if majority of the pixels are in this range, it will look, I'll show you the example on the computer in a second, but anyway, it will not look very clear, right? Okay, now let me ask you this. If we apply the contrast technique that I showed you on my laptop, will it help this picture look better?
It will become more dark.
More bright, because remember it's above the half value, so it will further increase these, but the relative difference will not change. Okay, 150 will become 160, 180 will become 190 as an example, right? So that won't help. So the proper way to do it is like, so if we take a look at the histogram of this, what will it look like? If this is the 0 to 255, meaning the pixel amount, the the value of the pixel, right? So if majority of the pixels are, so it might look something like this. This may be 150, this may be 180. I mean, it will not be zero, it will be low. You know, some pixels will be all over the place, but majority of them are over here. So this is what the histogram will look like, right? But for us to be able to clearly see the difference between, you know, some of the background and so on, or be able to see the edges clearly from the background, what we need is we need a higher distinction. So we need to widen it. Okay. So in other words, a better looking picture will be where the histogram looks like this. Okay. So we widen this quite a bit so that we can see the differences in the pixels, right? So let me go to the computer, show you the algorithm, and as part of your first assignment, you'll be programming this histogram equalization. Okay. In the beginning, if you get stuck, don't worry, I understand some of you are new to programming. So try it for a few days, then come and see me and I'll give you the solution, okay? And you won't lose any penalty. But my goal is gradually you keep learning, you keep getting better at programming so that by the half of the course you're able to do some advanced things by yourself, okay? Okay, so as I had briefly shown you, in my opinion, Wikipedia does a great job explaining the algorithm. So when you're programming it, you'll follow all the steps Wikipedia tells you. Okay. So if you just search for a histogram equalization, go to the Wikipedia article, and I'll take you through a simple example that they give us. Okay. So let's say we have a very small image, an 8x8 image, right? Okay, and these are the grayscale pixel values. Okay, so anyway, if we try to compute the histogram, right? This will come out to be like this. The pixel value 52 is only appearing one time. Pixel value 55 is appearing 3 times. Let's verify. If you take a look at pixel value 55, here's one, sorry, where my mouse is. Here's another one, 55, and here's another one, 55, where my mouse is, right? So 3 values only. So same way if you go through, verify it, 58 appears 2 times, 59 appears 3 times, and so on. So 64 and so on, and for example 73 appears 2 times, right? And we go through all the data that we have. So this is the count of the value of the pixel that appears that many times. Okay, so once we have created this table, right, then what we do is we compute what's called the cumulative distribution, the CDF. Okay, and the way CDF is computed is we start with the lowest value pixel, okay, which is 52, and we start with the count of 1, so 52, 1, right? Then if you take a look, how many times 55 appeared? 3 times, right? In the cumulative, what we are trying to do is we are just keep adding these numbers. So the cumulative value up to 55 will be whatever it appeared before, meaning 1 plus 3. So the cumulative value up to 55 is 4. Okay. Very similarly, what was the next number? 58, 2. So what will be the cumulative value up to this point? 1 plus 3 plus 2, 6, right? And same way, 1 plus 3 plus 2 plus 3, 9. So for 59, it should appear 9 in the cumulative CDF table. So 59, you can see 9, right? So the middle column is nothing but simply running sum of the count of the pixels that appeared, right? Okay, so then we create one more column which is called the equalized value. In the equalized value, the formula is like this. Okay, whatever was the CDF value, we subtract it from the minimum CDF value. Okay, what's the minimum in this table? 1. The minimum CDF value is 1. Okay, the CDF value, for example, could be 15, could be 17 at a given point, right? So, given CDF value minus the minimum divided by m times n. M is the number of rows, number of columns, or rows times columns. Okay, so in our case it was 8 by 8 example, so this will be 64. Okay, and then L is the number of levels. On a grayscale it's 255, so this will be 255, right? So let's pick an example. Let's see, where did it go? Okay, CDF for 78 is 46. Okay, let's go to 78 in our table. This is the 46, right? So now, how did we come up with 182? This is what we are trying to determine. So 46 was the value, CDF value for 78. So take a look over here. This will be 46 minus CDF min will be 1.
45 upon 18 to 8, that's 64.
No, I mean, what about the bottom? M times n will be
82.
64, right?
Yeah.
Okay, minus 1.
1.
And then multiplied by 255 plus 1. Okay, so anyway, this is what they did. 46 minus 1 divided by 63 multiplied by 255. And then if we go, it comes out to value of 182. And this is what we, where did it go? 78. So the value 78 became 182. Okay. So you can see there was a big change in it. And this is what, by the way, this is what we'll display in the final image. Okay. So essentially what it's doing is, okay, this was the original histogram. You can see majority values are on the low end, but then it's spread them out. Okay. Very similarly, if you take a look at this picture that they showed, okay, a lot of the values here, this red one tells you are between 100 and 120 maybe and 200, right? So it's a little bit on the brighter side, but to distinguish between, you know, some of the trees and the hill and it's kind of hard to do that, right? After we apply the same formula to every pixel, meaning we compute the histogram, compute the CDF, then compute the HV, which is the equivalent value, and we apply it, now you can see it's a lot clearer. And this is what happens to the histogram, so it widens it, okay? So you will try that, and you'll try to write this code yourself, okay? There are some examples available on the internet too. You can search for it. My suggestion would be, you know, because you want to gradually become really good yourself, don't take the easy route from grading point of view. It doesn't matter whether you did it or you did not do it. Okay, first 2 months, like I said, even if you didn't do it, I'll give you my code. Okay, give it your best shot, and if you get stuck any point, feel free to stop by. I'll help you make progress so that you keep learning, right? So to summarize, your first assignment is to redo this histogram equalization by following the Wikipedia article and create this yourself and redo the image processing application that I showed you over here so that you know how to basically crop images, rotate, shift, and so on. Okay. Now let me cover a tiny bit of a theory for the next part, and then we'll do some more involved processing in the next lecture. Okay, so whatever we did was so far is extremely basic. Okay, now let's go to a tiny bit more involved things. Again, it's not difficult, but as you will see, if you take a look at the final code or the final answer, it will always be simple. But the question is, how did we get there? Majority of the time, there will be some kind of a math involved behind that concept. So the next topic is very important. We'll be looking at convolution filters. Okay. So filters are basically some operations that we apply to an image to enhance certain features of the image. For example, we may be interested in, if somebody gave us an image like this, that we wanted to enhance the edges so that we can clearly see where the edges are, as an example, right? So what we'll do is, in these type of filters, we'll come up with a kernel, okay? And we'll apply this kernel to all the pixels in the image, and then it will accomplish whatever that kernel was supposed to do. Okay, sometimes we have a need to sharpen the images. Sometimes we have a need to make the edges blur out with the background. Okay, so we may be interested in sharpening or blurring, or like I said, many different possibilities over here. So gradually we'll develop the math so that we can come up with the kernel of ourselves. Okay, I need to explain to you the concept of the convolution. And once you understand it, then like I said, we'll apply it to developing the kernels of ourselves. Okay, now if you have an electrical engineering background, just like computer scientists know algorithms and data structures inside out, electrical engineers know convolution inside out, right? But some of you are coming from EE background, computer science, computer engineering background. So let me show you just the idea of convolution first, then we'll go apply it to creating kernels of ourselves. Okay, so a couple of fundamental concepts that you should know. Okay, if you are given a linear system, or if you're confused what's a linear, don't worry about the linear for right now. Pretty much all systems in nature behave like this. If you give it an input, pretend this is a time domain system. So forget the images for the time being. So if I give it a signal x of t, some output y of t, so it will produce some y of t, right? Okay, now let me take the same system and feed in an input delta of t. So delta of t is called the impulse. Okay, if I draw this delta of t, it looks like this. So if this is x, this is y. So typically this is what delta of t looks like. Okay. What's the magnitude? So it does not have any value other than the 0. Only at the point 0 it has some magnitude. What's the magnitude of? No. Okay. It has an infinite magnitude actually. And like the width is also 0. So the property for the delta is if we integrate from minus infinity to infinity, then we get the 1, right? Okay. So if we apply delta of t to our input in any system that we have created, suppose whatever output it gives, we call it h of t. Okay, this h of t in the technical terminology we call impulse response. Okay, because this delta of t is called the impulse, right? Okay, so all systems in nature behave it such that if h of t is the output when we gave delta of t as an input, then if we give it any other input, not delta of t, but it could be some signal which may look, anything like this, then the output is always a convolution of x of t and h of t. So all systems in nature, including imaging systems that we will create, behave this way. Okay. So once you know the h of t, then it will help us determine the output for any given input by simply doing the convolution. Okay. So what exactly is the convolution? The convolution is mathematically represented as x of tau, h of t minus tau, d of tau, or also minus infinity x of t minus tau, h of tau, d tau. So both are the equivalent. Okay, so the actual computation is done like this. Okay, so now let me pick an example. I'll go through the math. Once you understand how it worked, then we'll develop a physical intuition. What exactly is this convolution doing? Okay, and then, like I said, we'll come to images. Once we have the idea, we'll be able to create our own kernels based on a particular need. Okay, so let's pick an example. Let's suppose we have two signals. Let's say x of t. And suppose x of t looks like this. 1 minus 1, 1. And suppose h of t looks like this. 4, 5, 6. And the values. Okay, so what I want to very quickly show you is how will we evaluate this convolution, and after we do the convolution, what will it look like? Okay, so let's take a look at this second equation over here. We'll try, both are equivalent. I can do it this way or this way. If you take a look at the second equation, first thing we need to do is come up with what is x of t minus tau. Easy way to do it is first do x of actually, let me make it so that it is a little bit easier for you guys to see. Let me change it so that, let's make it like this. Because you'll be able to see that as I flip it, you'll be able to see it clearly. So let me make it 0, 1, 2, and 1 here. So this is my x of t in the beginning. Okay. So to be able to evaluate x of t minus tau, what we do is, we see this is on the t scale. we make it on the tau scale, and then flip it. So x of minus tau, basically what will happen is, like, it will mirror on the y-axis, so this will look like this. And it will become, like I said, tau scale now. Okay, right? So all I did was think of x, t, I made it minus t, basically became this, and then changed t to a tau. Nothing special. Okay, so this is, so far I have just x of minus tau. Okay, now let's go one step further. And now let me show you what of x of t minus tau look like. Okay, t minus tau basically means there's a, this t basically means there's a shift involved. Okay, so if I made it like this, pretend this is t. So it got shifted to the right by an amount t. T could be 0.1, 0.2, 8, 10, whatever, right? If this is t, then what will this point be? T minus 1. Because remember it was a difference of 1. What will this be? T minus 2. Okay. So if you take a look at the equation of this line, let's take a look at the equation of this line. Okay, the equation of this line will be tau plus 2. Okay, this will be the equation of this line. Okay, why tau plus 2? Like, for example, no, tau minus negative 1. Let me see. Sorry, this will be minus tau, right? Because if tau is 0, value is 0. If tau is negative 1, the value is 1. Okay. Anyway, if I go over here, then the equation will be tau plus 2. Because if you take a look, if I substitute negative 2 for the tau, it's 0. If I substitute negative 1, it becomes 1 over here, right? Okay, anyway, once we have the equation for the line, then as you can see, what we need to do is we basically need to, as we change the t, you will see this will start to move and slide. So, so now let me draw one more picture over here. Let's see. Okay, 4, 5, 6. Okay. Okay. So this was the case when t is 0. Okay. If t is 1, this will move 1 to the right. T. So what will happen when t is exactly 4? Actually, make it a little better so that. Okay, so this is basically t equal to 4. Now this thing is basically sliding and has appeared over here, right? So this is basically now h of tau, and this part over here is x of t minus tau. Okay, now what are we doing? We are multiplying the two and integrating, right? If I multiply these two, what will be the result? 0. There's no overlap. Because remember, integration is simply area under the curve, right? So the answer, so here's my convolution answer. Okay, so it will be completely 0. Okay, now I make the t between 4 and 5. So suppose it goes like this. Right, so t is over here. So as you can see now, as I multiply the two, is there some area involved? Yeah. So there will be some number produced, right? As t moves to 5, what will happen?
The value will increase.
What will be this value? What? Okay. How much is from here to here?
One.
So if this is 1, this is 1, what will be this total area? 1. Good. What will be this area? Yeah. So as you can see at t equal to 4, it started to increase. T equal to 5, it became 0.5. Everybody agrees?
Yes.
Okay. Now let's go to further. Okay, suppose it has moved over here. So as you can see, the area will be something like this. Is it more than 0.5?
Yes.
Okay. What will happen
That's it.
when it's moved over here?
One.
Area will be 1, right? Then as we keep sliding, it will start to reduce. When will it be completely done?
At 6.
At 8. Okay, so now you can see what the convolution result will look like. 4, 5, 6, 7, 8. What's the value at? So it will look something like this. Okay, what's the value at 5? Okay, actually, this should be a little bit better. Okay, so this is basically 0.5. Okay, so what is it telling us? Okay, now let's try to develop an intuitive meaning of convolution. Okay, convolution between two things basically tells us when an overlap occurs between the two things. Okay, so remember, convolution basically is flip one signal and start sliding it and see is there an overlap. The overlap was produced when it exceeded a little bit 4, right? Because remember, right? And then it became maximum at what value? When t was 6, then it became the maximum overlap, right? So the way this concept is very useful to us is, as you will see, okay, yeah, one of them is object detection. So let's say there's a soccer ball over here. Okay, suppose you have a picture of a soccer ball. Okay, and you wanted to know where is the soccer ball in this image. What will you do? Convolution of the two will tell you the position where the maximum overlap occurs. So that's one application of convolution. Okay, there are other applications as well. Okay, so for today, let me give you one more concept, and then in the next lecture, I'll tie it to developing kernels for our imaging applications. Okay, so the second concept you want to remember is okay, if we are given a system, we give it some input x of t, output as y of t. How is y of t related to the input? It's always x of t convolution with the impulse